Our brain is truly marvelous. Billions of neurons communicating each fraction of a second. The question is, how could it evolve? Welcome to Psyched. Previously, we have seen how vision evolved, such that organisms can recognize potential resources and dangers from afar. Although vision greatly benefits survival, its potential is limited, since a great amount of information about our surroundings is invisible. To overcome this limitation, together with the arrival of sight, we also observe the development of taste and smell. Despite being processed by different organs, both taste and smell receptors detect chemicals referred to as tastins and odorants. Gustation, which is our sense of taste, is specialized in the recognition of chemicals commonly found in foods after breaking these foods down by chewing or sucking. This helps us recognize whether the things we eat are rich in nutrients and benefit our survival, or whether these foods are no longer edible and would be detrimental for our survival. Olfaction, that is the sense of smell, is specialized in recognizing other airborne chemicals, which helps us finding resources and avoiding predators, as well as signaling social and sexual interests. Particularly volatile chemicals, picked up by smell, provide information about distant necessities, as chemicals travel more easily through the air. Within the animal kingdom, the human sense of smell and taste are far from impressive. With at least 10 times more olfactory receptors, sense of smell of dogs is far superior compared to ours. Still, elephants trump even that, and they can detect a smell that is more than 10 kilometers away. On the other hand, catfish have an amazing sense of taste. With taste buds all over their body, rather than just on the tongue, catfish have the ability to taste protein-rich foods from a distance in murky waters. However, despite human smell and taste not being anything special, it shouldn't be underestimated. Both senses can evoke strong emotional reactions, such as disgust. Furthermore, memory of specific odors and tastes can be strong and long-lasting. For example, known as the Garcia effect, a single encounter with an aversive taste can imprint a memory of never eating that food again. And smells can evoke recollection of memories of a single event that is more than 10 years ago, which otherwise could not have been recalled. So, how did taste and smell evolve? And how did a connection between these senses and brain processes such as emotion and memory develop? Perception Chemicals goes back far in our evolutionary history. As with responsiveness to light, responsiveness to odorants and tastins can be observed in single-celled organisms. However, these traits have become far more sophisticated in multicelled animals, who developed specific receptors that pick up chemicals around us. Although humans cannot smell underwater, due to the risk of drowning, olfaction did first evolve in our underwater living ancestors, some 700 million years ago. It is not long after that the olfactory bulb evolved. This is the brain structure that receives direct information from smell receptors. This structure can still be found in humans and forms, together with areas in the brainstem, one of the most ancient structures of our brain in evolutionary terms. Talking about the brainstem, it is here where first brain nuclei evolved that connected to our taste buds, specifically in the pons and the medulla. Whereas our fish-like ancestors developed olfactory receptors that could detect water-soluble chemicals, the first tetrapods that arrived on land developed olfaction receptors that primarily detect volatile chemicals. Indeed, this transition from detecting odors above and underwater can be observed in many living amphibians today, which have the ability to detect smells on land and underwater. Losing the sense of smell underwater has led in some mammals that later readapted to an aquatic lifestyle, such as many species of dolphin, to completely lose their sense of smell. Other land animals, however, developed their olfactory system to thrive in a world rich of smells. Together with the evolution of detecting airborne chemicals, we see the development of a nose. Inhalation through the nose holes allows for a concentrated influx of chemicals. These particles gather in the nasal cavities and are kept there for longer with nasal mucus. Keeping these odorants in place increases the chance of being picked up by olfactory receptors, and thus improves the ability to detect smells. Not only did the exterior of animals change, the brain evolved as well. With the arrival of the first mammals, some 200 million years ago, new brain structures emerged that amplify the importance of our sense of smell and taste. Specifically, the limbic system evolved. This is a complex brain structure involving a dozen or so regions that couple our senses to emotion and memory. Indeed, the limbic system contains structures such as the hippocampus, that is crucial for long-term memory, and the amygdala, which is paramount in emotional processing such as fear and threat. Importantly, brain structures involved in the processing of smell and taste, the primary olfactory and gustatory cortex, are part of this limbic system. This explains why both senses evoke such strong memories and emotions. The limbic system is also important for fight or flight responses, and is such important for survival. It is therefore that many mammals possess an impeccable sense of smell, and have the ability to detect more than 10,000 odors. As such, smell has become more important than just for finding food. For many mammals, it is the driving force in fleeing from dangers, finding potential mates by detection of pheromones, and marking territories. For one group of mammals, that is, primates, who specialized in a lifestyle that is primarily located in trees, sense of smell has become less important. Distinguishing ripe from unripe fruits was enabled through the development of color vision. And locating predators, such as fast-moving raptorial birds, is easier by sight compared to smell. As such, the reliance on smell gradually decreased in primates over the last 60 million years. Yet, to not lose the ability to find nutrient-rich foods, primates developed a liking for sweet, since their diet mainly revolves around eating fruits. Additionally, to detect rotten fruits, natural selection promoted the advancement of taste receptors detecting bitter tastes. By coupling bitter to an aversive reaction, spoiled foods can be avoided. This yet again shows the advantage of coupling brain regions related to taste to other brain regions that are involved in emotional processing, such as the emotion of disgust. Despite the sense of smell being less keen in primates compared to other mammals, the interaction between smell and taste is ever present, which is explained by the observation that both sensations are coupled to brain regions within the same network. Although the gustatory system encodes only 5 tastes, namely sweet, sour, salty, bitter, and umami, we have a rich perception of various flavors. These complex tastes occur due to an interaction with our olfaction system, with its capability of perceiving thousands of chemicals. Furthermore, sensory and thermoreceptors in the mouth provide additional information about texture and temperature of food, the latter being ever more crucial since the discovery of fire and the human ability to cook food. Since primates depended less on olfaction, their ability to detect invisible dangers and predators by smell dwindled. Another sense had to step in to keep our ancestors safe, which is the sense of hearing. This we will cover the next time. We hope you enjoyed this episode, and we hope to see you the next time. Bye bye.